Hi, dear friend. You've found a quiet place to rest and dream. Tonight, we'll drift through the final moments of ancient stars where endings become beginnings and light transforms into something eternal. Let yourself settle now. Feel the weight of your body against whatever supports you. There's nowhere else you need to be, nothing else you need to do. The day has released you. The night welcomes you. And here, in this moment, you're invited to journey with me through the silent gardens where stars go to rest. I'm floating here, suspended in the kind of darkness that feels less like absence and more like presence. The void around me isn't empty at all. It's filled with stories written in light that left its source thousands, sometimes millions of years ago. Each photon that reaches my visor has traveled so far, carried a message across such impossible distances that I can barely comprehend the patience required for that journey. You can let your breathing slow now. There's no rush. Time moves differently out here. Ahead of me, perhaps a dozen light years away, though distance loses meaning in places like this, I can see the fading glow of what was once a giant. A star that burned bright when Earth was young, when the first simple cells were learning to divide in warm, shallow seeds. That star has been dying for longer than humans have existed, and yet its death is so gradual, so elegant, that it looks almost peaceful from here. The light it gives off now is softer than it was, less fierce. It's shifted toward the red end of the spectrum, stretched out by its own expansion like a sigh that never quite ends. Red giants, we call them. Stars that have exhausted the hydrogen in their cores and begun fusing helium instead, swelling outward in the process. Imagine a heart growing larger as it grows older, beating slower but somehow deeper. Let that image rest in your mind. This star, this ancient giant, has already consumed whatever planets once orbited close. They didn't explode or shatter dramatically. They simply dissolved into the expanding outer layers of their sun, returning to the stellar matter from which they formed. Dust to dust, but on a cosmic scale. There's something fitting about that, something that feels less like ending and more like returning home. I adjust my position using small bursts from my suit's thrusters. The sound is so faint, it's almost imaginable. Out here, silence is the default. Even explosions happen in perfect quiet. Even the death of stars unfolds without sound. Though if you could somehow hear it, I imagine it would sound like the lowest note ever played, a frequency below hearing, felt only as vibration in the chest. You don't need to hold on to these words. Let them flow through you like starlight through. The giant star before me will shed its outer layers soon, astronomically. Perhaps in another 1,000 years, perhaps in 100,000. Time is patient with stars. It doesn't hurry them toward their conclusions. The outer shells will drift away slowly, pushed outward by the radiation pressure from the hot core within. Those shells will form a nebula, a cloud of glowing gas shaped by magnetic fields and stellar winds into forms that might look like flowers or butterflies or hourglasses. Humans have photographed these planetary nebulae, as we call them, though they have nothing to do with planets. We've given them names. The Ring Nebula, the Helix Nebula, the Cat's Eye. Each one is a portrait of a star's final breath, frozen in light and color, beautiful beyond words. Right now, at this moment, there are thousands of these nebulae scattered throughout our galaxy. Each one marks a place where a star has recently died. recently in cosmic terms. Some of them have been glowing for tens of thousands of years. Others are so new their light hasn't reached Earth yet. Somewhere, right now, someone might be looking up at a star that no longer exists, seeing the ghost of something already gone. Let your eyes close if they want to. You're safe here. The core that remains after the outer layers drift away will be extraordinary, dense beyond imagination. A white dwarf, we call it, though there's nothing dwarfish about it. An object with the mass of our sun compressed into something of Earth. Imagine taking all that stellar matter, all that burning weight, and squeezing it down until a teaspoon of it would weigh as much as an elephant. That's the density we're talking about. Matter pressed so tightly that atoms themselves are crushed, their electrons stripped away and packed between the nuclei like puzzle pieces forced together. These white dwarfs glow from leftover heat. They're not fusing anything anymore. They're not generating new energy. They're simply cooling slowly, releasing the thermal energy they've stored over billions of years. It takes so long for them to cool that the universe isn't old enough yet for any white dwarf to have gone completely cold. Every single one that's ever formed is still glowing, still warm, still holding on to that last bit of stellar fire. There's something profoundly moving about that, something that speaks to persistence, to the way heat lingers, the way warmth doesn't disappear instantly, but fades gently into the background. If sleep comes now, let it come. The story will continue, and you'll be held by it. I'm drifting closer to a different kind of remnant now. This one is more violent in its. This is what's left after a supernova, after a star much larger than our sun reached the end of its fusion fuel and collapsed in on itself before exploding outward with the force of a billion suns. The debris field is enormous. It stretches for light years in every direction, an expanding cloud of gas and dust moving outward at thousands of kilometers per. Even now, centuries or millennia after the initial explosion, the material is still traveling, still carrying the momentum from that catastrophe. But catastrophe is such a harsh word for something so beautiful. The colors here are unlike anything you'd see. There's a deep red from hydrogen that's been excited by shocks, glowing as its electrons jump between energy levels. There's blue from oxygen, which requires more energy to excite and therefore marks the hottest regions. And there's a subtle purple where the two mix and cool meet and blend. Threading through the gas are delicate filaments, structures that look almost deliberately crafted. They're formed by magnetic fields that were present in the original star, now stretched and twisted by the explosion into patterns that resemble neural networks, or the branching of the universe. Left to its own devices, seems to prefer certain shapes. Certain geometries recur at every scale, from the firing of neurons to the structure of galaxies. Your mind can wander now. There's no need to follow every detail. Inside this supernova remnant, I know, though I can't see them directly, there are exotic elements that weren't present anywhere in the universe before this star. You see, the fusion that happens in a star's core during its normal life can only build elements up to iron. Hydrogen fuses into helium, helium into carbon, carbon into oxygen, and so on, climbing up the periodic table until you reach iron, which is the most stable nucleus, the one that requires more energy to fuse than it releases. To make anything heavier than iron, you need the extreme conditions of a supernova. You need neutrons to be slammed into iron nuclei so fast and so forcefully that they stick. building up heavier and heavier elements before there's time for decay. Gold is made this way. Platinum, uranium. Every atom of gold in every ring ever worn was forged in a supernova explosion. Every bit of iodine necessary for your thyroid to function came from a dying star. We are quite literally made of stardust, not metaphorically. Actually, the calcium in your bones was formed in a star, the iron in your blood, the oxygen you're breathing right now. All of it came from stars that lived and died before our sun was born, that scattered their enriched material into the cosmic clouds from which new stars and planets would eventually form. Let that settle into you. You are made of the universe. You are not separate from it. The supernova remnant I'm passing through now is called Cassiopeia A, though I don't expect you to remember that. It's about 340 light-years from Earth, and the explosion that created it happened about 340 years ago from Earth's perspective. The light from the explosion reached Earth in the 1600s, though I don't think anyone recorded seeing it. It might have been obscured by dust, or simply overlooked. At the center of this expanding debris field, invisible beneath layers of gas and light, is a neutron star, an object even more dense than a white dwarf. Imagine taking more mass than our sun and compressing it into a sphere just 20 kilometers across. The density is so extreme that protons and electrons are forced together to form neutrons, and those neutrons are packed so tightly that a single cubic centimeter weighs as much as a mountain. The surface gravity on a neutron star is about 2 billion times stronger than Earth's. If you could somehow stand on one, which you couldn't, you would be flattened instantly into a layer of atoms less than a millimeter thick. Time itself moves differently in that intense gravitational field, running slower near the surface than it does far away. Some neutron stars spin hundreds of times per second, rotating so fast that their surfaces are moving at a significant fraction of the speed of light. They're called pulsars when they emit beams of radiation from their magnetic poles, beams that sweep across space like cosmic lighthouses. Each time the beam points toward Earth, our telescopes pick up a pulse, rhythmic, reliable. Some pulsars are so stable that they rival atomic clocks in their precision. You don't need to understand it all. Just let the wonder of it wash over you. I've adjusted my trajectory now, moving through a quieter region of space. The light here is dimmer. The stars more distant. This is the kind of darkness where you can see deeper into the universe because there's less nearby light to overwhelm your vision. Looking out into this darkness is looking back in time. Light has a speed limit, about 300,000 kilometers per second, which sounds fast until you consider the distances involved. The light from a star 10 light-years away left that star 10 years ago. The light from a galaxy 1,000,000 light-years away left that galaxy 1,000,000 years ago. When we look at distant objects, we're not seeing them as they are now. We're seeing them as they were when their light began its journey toward us. We're looking at the past, preserved in photons, carried across the void to arrive at our eyes. There's something profound about it. The universe has a built-in archive of its own history, written in light, available to anyone who takes the time to look up. Let your thoughts drift like stars across. The farthest objects we've detected are about 13 billion light-years away. Their light has been traveling toward us for almost the entire age of the universe, which is about 13.8 billion years old. Those galaxies were young when their light left them. They've aged 13 billion years since then, evolved, possibly merged with other galaxies, perhaps watched as civilizations rose and fell on planets we'll never know about. But we see them as they were then, young, bright, full of hot blue stars that burn fast and die young. Out here, drifting among the remnants of stars, I'm struck by the continuity of it all. Nothing is truly lost. Everything transformed. The hydrogen that formed in the first moments after the Big Bang is still around most. It's been through stars, perhaps multiple times. It's been part of nebulae and planets and comets. Some of it is in you right now, part of water molecules, part of organic compounds, part of the chemistry that lets you think and feel and dream. The universe recycles itself endlessly. Death feeds birth. Endings enable beginnings. There's a supernova remnant ahead of me now that's much older than Cassiopeia A. This one is thousands of years old, and it's expanded so much that it's become thin, almost transparent. The shock wave has slowed as it's encountered interstellar material. The colors have faded, but it's still there, still visible, still marking the place where a star once ended. In another few thousand years, it will have merged completely with the surrounding interstellar medium. The material will be indistinguishable from the general background of gas and dust that fills the space between stars. And that material will eventually collapse under its own gravity to form new stars, new planets, new possibility. The calcium atoms that were once fused inside a massive star will end up in the rocks of a distant world. The carbon will become part of organic molecules, perhaps even part of living things. The iron will sink to the core of a planet, generating magnetic fields that protect whatever surface might exist there. If your mind wanders, let it. There's no wrong way to rest here. I think about the civilizations that might have watched these supernovas, not the explosions we see now, but the actual events, the moments when stars collapsed and rebounded in cataclysmic death. If there were planets orbiting nearby stars, if there were beings looking up at their night skies, they would have seen a new star appear, brighter than anything else visible, bright enough to cast shadows at night, bright enough to be seen during the day. Ancient humans witnessed supernovas too. Chinese astronomers recorded a guest star in 1054 CE that was visible for weeks. That was the explosion that created the Crab Nebula, which is still glowing today, still expanding, still powered by the pulsar at its heart. The light from that explosion traveled about 6,500 years to reach Earth. So the actual event happened around 5500 BCE, when humans were just beginning to develop agriculture, just starting to settle into permanent communities. That star exploded before writing was invented, before the pyramids were built, before metalworking. And yet its light reached Earth at a time when civilizations were advanced enough to record it, to wonder about it, to incorporate it into their understanding of the heavens. There's a continuity there too, a connection across vast spans of time and space. You are safe here. You are held by the universe itself. Some stars don't explode at all when they die. The ones smaller than about 8 times the mass of our sun will never go supernova. They'll swell into red giants, shed their outer layers, and leave behind whites. No explosions, no supernovas, just a gentle dissolution, a slow fade into a cooling ember that will glow quietly for billions or trillions of years. Our own sun will die this way. In about 5 billion years, it will exhaust its hydrogen fuel and begin fusing helium. It will expand, possibly engulfing Mercury and Venus, possibly reaching Earth's orbit. The oceans will boil away. The atmosphere will be stripped. Everything we've built will be vaporized, but that won't be the end. The atoms that make up Earth will still exist. They'll be part of the expanding outer layers of the sun, drifting outward into space. And eventually, they'll be incorporated into new stellar systems. The carbon in your body might end up in a planet orbiting a star that hasn't formed yet. The oxygen might become part of water ice on a comet. The iron might sink to the core of a world where new forms of life evolve. Nothing ends. Everything continues. The silence out here has texture. It's not the absence of sound, but the presence of something deeper, something that exists beneath sound, beneath language, beneath thought itself. I float through it like a leaf drifting downstream, carried by currents I can feel but not see. Let your mind rest in that silence too. There's no need to grasp at anything. Ahead of me, scattered across several light years of space, are the remnants of a star cluster that formed together billions of years ago. Dozens of stars born from the same molecular cloud. Siblings in the truest sense, all emerging within a few million years of each other. They've drifted apart since then, pulled in different directions by the tidal forces of the galaxy, by gravitational encounters with passing objects, by the simple fact that space is vast and orbits are never perfectly stable. Some of those sibling stars still exist, still burning their hydrogen, still lighting up small patches of the universe. Others have already died, leaving behind the artifacts of their existence. White dwarfs cooling in the darkness, neutron stars spinning impossibly fast. Perhaps even black holes, though those would be invisible to me, detectable only by their gravitational effects on nearby matter. Each of these stars lived its own life, followed its own path through the galaxy, experienced its own unique journey from birth to death. And yet they all began together, condensed from the same cloud, made of the same material, subject to the same physical laws. There's something almost familial about that, something that reminds me of human siblings, born into the same family but growing into different people, taking different paths, ending up in different places. You can let your thoughts wander like following connections, making associations, not forcing anything. The molecular cloud that gave birth to that star cluster no longer exists. It was used up in the process of star formation, converted from diffuse gas into dense stellar cores. The leftover material was either incorporated into planets and asteroids and comets, or blown away by the intense radiation from the newly formed stars. This is how star formation works. Gravity pulls gas together, the cloud collapses. The center heats up from compression. Eventually, if there's enough mass, the core reaches temperatures and pressures high enough for hydrogen fusion to begin. And then there's a star. It sounds simple when described like that, but the actual process is incredibly complex. The collapsing cloud fragments into multiple cores. Each core might form its own star, or it might merge with another core. Magnetic fields thread through the gas, resisting the collapse in some places, channeling it in others. Shock waves from nearby supernovas might trigger the collapse or disrupt it. Star formation is chaotic and messy and beautiful, just like most processes of creation. The stars that form in clusters like the one I'm observing tend to be bound together by their mutual gravity, at least initially. They orbit around their common center of mass, a slow, graceful dance that can last for hundreds of millions of years. But the dance eventually ends. Gravitational interactions eject some stars from the cluster. Others escape when they happen to pass close to another star and gain just enough velocity to. After a few billion years, most star clusters have completely dissolved. Their member stars are scattered across the galaxy, indistinguishable from stars that formed alone or in different clusters. The family has dispersed. The siblings have lost touch, but they're still related, still made of the same stuff, still carrying the signature of their common origin in the ratios of their elements, in the patterns of their motion. Let yourself feel supported by whatever holds you. You are safe and held. I'm adjusting my trajectory again, following a path that will take me past a particularly interesting object. It's a pulsar, a rapidly rotating neutron star that emits beams of radiation from its magnetic poles. Those beams sweep across space like lighthouse beams, and when they point toward Earth, our radio telescopes detect a pulse. This particular pulsar rotates 33 times per second. 33 complete revolutions in the time it takes you. The surface of the neutron star is moving at about 10% of the magnetic field is 1 trillion times stronger than Earth's. And yet, despite these extremes, the pulsar is slowing down, very gradually, almost imperceptibly, but each rotation takes a tiny bit longer than the star is losing energy through the radiation it emits, and that energy loss translates into slower rotation. In a few million years, it will have slowed enough that the radiation emission stops. It will become a regular neutron star, still incredibly dense, still possessing an intense magnetic field but no longer pulsing, no longer sending out those regular signals that let us know it's there. Eventually, the magnetic field itself. Over time scales we can barely calculate, the organized structure of the field will break down, dissipating into heat, and the neutron star will be left as nothing more than a ball of densely packed neutrons, cooling slowly, fading into the cosmic back. But that's trillions of years away. Right now, this pulsar is still young and spinning fast, broadcasting its presence across light years of space. You don't need to hold on to these details, just let them wash over you like waves. The radiation emitted by pulsars isn't just radio waves. Some pulsars also emit X-rays and gamma rays, the most energetic forms of light. These high-energy photons come from particles being accelerated to nearly the speed of light by the pulsar's intense magnetic field. Electrons spiral along the magnetic field lines, emitting synchrotron radiation as they curve. If you were somehow close to a pulsar, which you couldn't survive, you would be bathed in this radiation. It would pass through you, ionizing atoms, breaking molecular bonds, destroying cellular structure. Death would be instantaneous and complete. And yet from a safe distance, pulsars are harmless, beautiful even. The pulses they emit are so regular that they were initially mistaken for artificial signals when they were first discovered in the 1960s. Astronomers briefly wondered if they had detected evidence of extraterrestrial intelligence deliberately broadcasting into space. But no, just neutron stars, just the natural behavior of matter under extreme conditions. The universe doesn't need intelligence to create patterns that look designed. Physics alone is sufficient to generate complexity and regularity and beauty. There's something profound about that, something that suggests the universe itself is creative, that the laws of physics are not constraints, but possibilities, guidelines for what can emerge from simple starting conditions. Let your breathing deepen. Let each exhale release a little more tension. I'm passing through a region now where the interstellar dust is particularly dense. It's not thick enough to obscure my view completely, but it does dim the light from distant stars, making them appear redder than they actually are. This is called interstellar reddening, and it's caused by dust grains preferentially scattering blue light while allowing red light to. The same phenomenon makes Earth's sunsets red. Blue light is scattered by the atmosphere, filling the sky with that characteristic daytime blue. But during sunset, sunlight has to pass through more atmosphere, and more of the blue light gets scattered away, leaving the reds and oranges to. Here in space, the effect is more subtle, but similar in principle. The dust grains are tiny, about the size of smoke particles, composed mostly of carbon and silicates with a coating of water ice and frozen organic molecules. These dust grains are actually quite important. They serve as surfaces on which atoms can meet and bond, forming molecules that wouldn't easily form in the gas phase. Water forms on dust grains. So do organic molecules like methanol and formaldehyde, the building blocks of more complex chemistry. When a molecular cloud eventually collapses to form stars and planets, these dust grains become incorporated into the new system. Some end up in comets and asteroids. Some become part of planets. And they bring with them the molecules that formed on their surfaces, seeding the new system with chemical complexity. Life, when it arises, builds on this foundation. The organic molecules delivered by comets and asteroids provide raw materials for the chemistry of life, not life itself, but the ingredients from which life might emerge. We don't know how common life is in the universe. We have a sample size of 1, which is not enough to draw any firm conclusions. But we do know that the ingredients for life are common. Organic molecules exist throughout the galaxy. Water exists in abundance. Energy sources are everywhere. The conditions that gave rise to life on Earth probably exist in countless other places. Whether life actually arises in those places, we don't yet know, but the possibility is there. The universe is not hostile to life. It's full of the raw materials and energy needed to support it. If sleep is near, don't resist it. Let it come naturally. The dust cloud I'm moving through is part of a larger structure, a giant molecular cloud complex that stretches for hundreds of light years. These clouds are the wombs where stars are born. They're cold, just a few degrees above absolute zero, and dense, at least by the standards of interstellar space, containing thousands or even millions of hydrogen molecules per cubic centimeter. That still sounds empty by Earth standards, where air contains about 10 to the 19th molecules per cubic centimeter, but in space it's remarkably dense. Within these molecular clouds, gravity is slowly winning its eternal struggle against pressure and turbulence. Regions of slightly higher density attract more material, becoming denser still. The process feeds on itself. Dense regions grow denser. Eventually, they collapse to form protostars, hot cores that will eventually ignite and become true stars. But not all of the cloud participates in star formation. Most of it remains as diffuse gas, too spread out for gravity to bring together. That gas will eventually be dispersed by radiation from the newly formed stars, or by shock waves from supernovas, or by the tidal forces of the galaxy pulling the cloud apart. Nothing in space is permanent. Even these vast molecular clouds, which can exist for tens of millions of years, are temporary structures. They form, persist for a while, and then dissipate. The material returns to the general interstellar medium, ready to be incorporated into the next generation of clouds. The cycle continues: formation and dissolution, birth and death, concentration. You are part of cycles too, waking and sleeping, breathing in and breathing out, tension and release. I've been thinking about time again. It's hard not to out here, where the usual markers of time don't exist. On Earth, time is measured by the rotation of the planet, by its orbit around the sun, by the phases of the moon. Days and months and years are natural units tied to celestial. But out here, those units lose their meaning. A day is how long? The time it takes for what to rotate? A year is measured against what orbit? Instead, time becomes something more fluid. I measure it by my own biological rhythms, by the cycles of waking and sleeping, by the slow consumption of my supplies, by the gradual change in the positions of stars relative to each other. But even biological time is unreliable in the absence of external cues. Without sunlight to reset my circadian clock, my body wants to drift toward a slightly longer day, closer to 25 hours than 24. I have to artificially maintain a schedule, forcing myself to sleep and wake at regular intervals. Time, I've come to realize, is not as absolute as it seems. It's a construct we use to organize our experience, to make sense of change and sequence. But the universe doesn't care about our time. It operates on its own scales, from the incomprehensibly brief existence of virtual particles popping in and out of existence in the quantum foam, to the incomprehensibly long cooling of white dwarfs. Both extremes are real. Both are part of the same universe. Time accommodates all of it. Let go of any need to track time. Just be present in this moment. The pulsar I passed earlier emits its radiation in a cone, like a beam from a spotlight. If the cone happens to sweep across Earth as the pulsar rotates, we detect it as a pulse. But if the cone points in a different direction, we never know the pulsar exists. This means there are probably many more pulsars out there than we've detected. We only see the ones whose beams happen to point our way at some time during their rotation. The rest remain invisible unless we happen to detect them through other means, like their gravitational effects on companion stars. The universe is full of things we can't see. Dark matter, which outweighs visible matter by about 5-1. Dark energy, which makes up most of the universe's energy density. Black holes, which emit no light at all. Rogue planets wandering through interstellar space, unlit by any sun. Our picture of the universe is necessarily incomplete. We see what we can see, detect what our instruments are capable of detecting, and infer the existence of the rest from indirect evidence. But that's okay. We don't need to see everything to appreciate the beauty of what we can. We don't need to understand everything to be moved by the mystery of existence. Sometimes the questions are more interesting than the answers anyway. Your mind can rest now. It doesn't need to understand, just experience. I'm approaching another supernova remnant now, this one much older than the others I've passed. The shock wave has slowed significantly, no longer plowing through the interstellar medium at thousands of kilometers per second, but merely coasting along at a few hundred. The material has mixed with the surrounding gas, blending in, losing its distinct identity. In another few thousand years, it will be indistinguishable from the background. The atoms forged in the supernova will have been dispersed so widely that no one looking at this region of space will be able to tell that a star once died, but those atoms will still exist. They'll still carry the signature of their origin in their isotopic ratios, in the proportions of different elements. A scientist analyzing a sample of interstellar gas might notice an unusual abundance of certain isotopes and conclude that the sample was enriched by a supernova, but they won't be able to point to a specific location and say, "There, that's where the star exploded." The evidence of the star's death will have been erased, at least visually, but its legacy will persist in the chemical composition of the galaxy, in the heavy elements it scattered, in the star formation it triggered. This is true of everything, really. We leave traces, influences, effects that ripple outward long after we're gone. Even when the direct evidence of our existence has faded, the consequences of our having existed, you will leave traces in the people whose lives you've touched, in the work you've done, in the small ways you've shaped the world you. Nothing is ever truly lost. It just transforms. Let that thought comfort you as you sink deeper into the oldest light we can see in the universe is the cosmic microwave background radiation, light that was emitted about 380,000 years after the Big Bang. Before that, the universe was opaque, filled with a hot plasma that absorbed and scattered photons before they could travel very far. But as the universe expanded and cooled, the plasma condensed into neutral atoms, and suddenly photons could travel freely. That moment, when the universe became transparent, is called recombination, and the light emitted then has been traveling through space ever since. We can still detect that light today, though it's been stretched by the expansion of the universe from visible light to microwaves. It's everywhere, coming from every direction, a faint glow that fills the universe, carrying information about the conditions in the early universe. When we map the cosmic microwave background, we see tiny temperature fluctuations, regions that were slightly hotter or cooler than average. Those fluctuations were the seeds of all the structure in the universe today. The hot spots became regions where matter accumulated, eventually forming galaxies and stars and planets. The cold spots became the voids, vast empty regions between galaxy clusters. Everything we see, including ourselves, grew from those tiny fluctuations in the early universe. We're the descendants of quantum fluctuations that occurred in the first fraction of a second after the Big Bang. There's something both humbling and magnificent about that. We're products of processes that began billions of years before Earth existed, before our sun existed, before our galaxy took its current form. We're not separate from the universe. We're expressions of it, patterns that have emerged from its fundamental properties. Let yourself feel that connection. You are part of something vast. The stars I can see from here, thousands of them scattered across my field of view, are all at different distances. Some are relatively nearby, just a few dozen light years away. Others are hundreds or thousands of light years distant, and the light from each of them left its source at a different time. I'm not seeing the galaxy as it is right now. I'm seeing a composite image made up of light from different eras, all arriving at my eyes at the same moment, but carrying information from different times. That star over there, bright and blue, probably still exists. Its light left it just 50 years ago, but that dim red star much farther away might have died already. Its light has been traveling toward me for 5,000 years. The star itself could have run out of fuel and collapsed into a white dwarf centuries ago, but I won't know about it for centuries more. This is the nature of looking outward into the universe. You're always looking backward in time. The farther you look, the further back you see. And if there's someone in a distant galaxy looking toward our galaxy right now, they're not seeing it as it is now. They're seeing it as it was millions or billions of years ago, depending on their distance from us. They might be seeing our galaxy during an era when our sun didn't yet exist, when Earth was still part of an undifferentiated cloud of gas and dust. Time and space are woven together in ways that defy our everyday intuition. The universe is stranger and more wonderful than we typically imagine. You don't need to fully grasp this. Just let it add to your sense of wonder. There's a phenomenon called gravitational lensing, where the gravity of a massive object bends the path of light passing near it. If the alignment is just right, the massive object can act like a lens, magnifying and brightening the light from something behind. We've used gravitational lensing to observe extremely distant galaxies that would otherwise be too faint. The gravity of a closer galaxy cluster acts as a natural telescope, bending and focusing the light from the distant galaxy. Sometimes the geometry creates multiple images of the same object, distorted into arcs or rings. It's beautiful and bizarre, a demonstration that space itself is curved by the presence of mass, that light follows the curvature of space-time. Einstein predicted this effect, along with many other strange consequences of general relativity. He showed that gravity isn't a force in the traditional sense, but a curvature of space-time caused by the presence of mass and energy. Objects don't orbit each other because they're attracted by a force. They orbit because they're following the straightest possible through curved space-time. A planet orbits a star because the star's mass curves space-time around it, and the planet is just following that curvature. It's difficult to visualize in 3 dimensions, let alone the 4 dimensions of space-time, but the mathematics works beautifully. And every prediction Einstein made has been confirmed by observation. The universe operates according to rules we can discover and understand, even when those rules are counterintuitive and strange. Let your eyes grow heavy if they haven't already. Let rest come naturally. I'm thinking about the atoms in this spacesuit I'm wearing. The metal and plastic and fabric that separate me from the vacuum of space. Every atom in this suit came from somewhere. The aluminum was forged in a star, the carbon in the plastics, the oxygen in the water I'm drinking. And before those atoms were in those stars, they were part of earlier stars, or part of the primordial hydrogen and helium that formed in the Big Bang. They've been recycled countless times through countless generations of stars and nebulae and planetary systems. Some of the atoms in my body in this suit might have been part of the same star at some point billions of years ago. They've been on different journeys since then, ending up in different places, but they started together, and someday they'll be separated again. The atoms that make up my body will return to the environment. Some will become part of other living things. Some will be incorporated into rock or water. Some will be launched into space and become part of the interstellar medium. The atoms that make up this spacesuit will eventually be disassembled, recycled, used for other purposes, and eventually those atoms too will return to space, to the cosmic cycle of creation and destruction. Nothing is permanent. Everything is in flux. And yet, the atoms themselves persist, endlessly transforming, but never destroyed. We are temporary patterns in an endless flow of matter and energy. And that's okay. That's exactly what we should be. Your breath is so slow now, so steady and deep. Perfect. The universe is about 13.8 billion years old. That's a long time by human standards, but it's just the beginning by cosmic standards. Stars will continue to form for trillions of years. The smallest red dwarfs, the ones that burn their hydrogen slowly and efficiently, will live for 10 trillion years or more. We're in the early universe still. The stelliferous era, it's called, the age when stars light up the cosmos. This era will last far longer than the time that's already passed. But eventually, star formation will cease. The available hydrogen will be used up or locked away in objects like white dwarfs and neutron stars and black holes, where it can't participate in new star formation. The last stars will form, burn, and die. And then the universe will enter the degenerate era, when the only sources of light are decaying stellar remnants, white dwarfs cooling in the darkness, the occasional flash when one captures matter from a companion and undergoes a nova explosion, but mostly just darkness. This era will last until the white dwarfs themselves finally cool to match the temperature of that will take about 10 to the 37th years, a number so large it's almost meaningless. After that comes the black hole era, when even protons have decayed and the only significant objects are black holes. These will gradually evaporate through Hawking radiation, taking about 10 to the 100 years for the largest ones to disappear. And then, the dark era, a universe containing only photons and neutrinos and maybe a few exotic particles we haven't discovered yet, spread so thin and diluted by expansion that interactions between them become vanishingly rare. That's the far future, the ultimate fate. Heat death, we call it, though it's really a cold death. Everything spread out and cooled down to the point where nothing can happen anymore. But that's so far away that it's almost abstract. Right now we're in the beautiful middle, when the universe is full of light and complexity and possibility. Enjoy this moment, this brief, precious era when stars shine and life exists, and the cosmos is knowable. Let sleep take you now, gently. You've traveled far tonight through space and time and thought. You've touched the infinite and found it welcoming. You've learned that endings are transformations, that death feeds life, that nothing is ever truly lost. Rest now in that knowledge. Let the universe hold you as you drift into dreams. The stars will keep watch. The darkness will keep you safe. And morning, when it comes, will find you renewed, refreshed, and grateful for the mystery and beauty of existence. Good night, traveler. May your rest be deep and your dreams be filled with stars. Let sleep come if it wants to. You don't need to stay awake. The largest stars, the ones more than about 20 times the mass of our sun, die in the most dramatic way possible. They don't just explode. They collapse so completely that they become black holes, regions of space-time where gravity is so strong that not even light can escape. The transition happens in seconds. The core runs out of fusion fuel and can no longer support itself against gravity. It collapses inward, compressing matter to densities we can barely calculate, until it punches through space-time itself and creates a singularity, a point where the laws of physics as we understand them break down. The outer layers fall inward and then rebound off the collapsing core, exploding outward in what we call a supernova. But at the heart, hidden behind an event horizon, the singularity remains. A black hole, a place where time stops, where space curves infinitely, where all our equations fail. And yet, even black holes aren't eternal. Stephen Hawking showed that they emit radiation, very slowly, gradually losing mass over incomprehensible spans of time. A black hole with the mass of our sun would take about 10 to the 67th years to evaporate completely. That's a 1 followed by 67 zeros. A number so large it makes the current age of the universe seem like the blink of an eye. But eventually, even black holes will fade. Even the most dramatic deaths will resolve into the background radiation of an old, cold, dark universe. Your breathing is slower now, deeper. That's good. I'm passing through a region rich with young stars now. This seems contradictory, to move from stellar death to stellar birth, but they're connected. These young stars are forming from the material scattered by previous generations of stars. The nebula I'm approaching is lit from within by dozens of hot blue stars that formed just a few million years ago. Around some of these stars, I can see the disks of material from which planets might form. Protoplanetary disks, we call them. Flat, rotating clouds of gas and dust held in orbit by the star's gravity. Over millions of years, the particles in these disks will collide and stick together, building up larger and larger objects, pebbles, boulders, planetesimals, eventually planets. It's happening right now, in real time, though the timescales are so long that we can't perceive the motion. But it's happening. New worlds are being born from the iron that will form the core of those planets came from a supernova. The water ice that will deliver oceans to their surfaces came from comets formed in the cold outer regions of the protoplanetary disk. And the oxygen in that water came from a star. The organic molecules that might someday become the building blocks of life will be delivered by asteroids and comets, and those molecules contain carbon forged in stellar furnaces. Life, if it arises on those worlds, will be made entirely of recycled stellar material, just like you. Let your body feel. Let yourself sink deeper into rest. There's a concept in physics called entropy, which is often described as disorder or randomness. The second law of thermodynamics tells us that entropy always increases in a closed system. Things tend toward disorder. Hot objects cool, organized structures break, stars burn out. But this isn't quite the full picture. Yes, entropy increases overall, but locally, temporarily, complex structures can. Stars themselves are low-entropy objects, highly organized, held together by gravity and powered by fusion. Planets are even more organized. And life is the most organized, most low-entropy thing we know of. We exist as temporary pockets of order in a universe trending toward disorder. We're not fighting the universe. We're part of its natural behavior, part of how it explores the possibilities available to it. Every star that dies increases the entropy of the universe, but it also enriches the interstellar medium with heavy elements, making possible a wider range of chemistry, a greater diversity of planetary types, more opportunities for complexity to arise. Death enables life. Disorder creates the conditions for order. You don't need to think about this. just let it settle into your awareness. I've been out here long enough now that my sense of time has become unreliable. Hours feel like minutes. Minutes stretch into eternities. There's no day or night cycle to anchor my circadian rhythms. No sunrise to mark new beginnings. Just the slow rotation of the galaxy, which takes about 250 million years to complete. Our sun has orbited the galactic center about 20 times since it formed. Earth has been around for about 18 of those orbits. Life has existed for maybe 15 orbits. Humans, anatomically modern humans, for less than 1,000th of one orbit. We're so new, so recent. And yet we've managed to figure out so much. We've decoded the life cycles of stars. We've mapped the structure of the galaxy. We've looked back to the beginning of the universe and forward to its possible ends. We're made of star stuff that has become aware of itself. We're the universe looking at itself, thinking about itself, trying to understand itself. There's something beautiful about that. Something that justifies all the struggle and confusion and difficulty. Let your thoughts slow. Let them become like stars drifting in the dark. The supernova remnants I've been passing through are nurseries as well as graveyard. The shock waves from the explosions compress nearby gas clouds, triggering the collapse that begins star formation. Without supernovas, star formation would eventually stop. The galaxy would slowly use up its available hydrogen, form it all into stars, and then go dark as those stars aged and died. But supernovas replenish the interstellar medium. They inject fresh material back into the galaxy. They trigger new generations of stars. They keep the cycle going. In about 4 billion years, our Milky Way galaxy will collide with the Andromeda galaxy. The two will merge over the course of several billion years, their stars passing through each other like ghosts, only rarely colliding because the distances between stars are so vast. But the gas clouds will interact, compressing each other, triggering an intense period of star formation. Our sun, if it still exists then, which it will be swept up in this merger. It might end up in a completely different region of the combined galaxy. Earth, if it still exists, which is less certain, will have a very different view of the night sky. But these things are so far in the future that they're almost abstract. The universe has time, so much time. You have time too. Time to rest, time to let go. There's a type of star called a magnetar, which is a neutron star with an incredibly strong magnetic field, the strongest magnetic fields we've ever detected. A magnetar's magnetic field is about a quadrillion times stronger than Earth's. If you somehow got within 1,000 kilometers of a magnetar, the magnetic field would be strong enough to disrupt the molecular bonds in your body. You wouldn't be killed by radiation or gravity. You'd be killed by magnetism, which would literally tear apart the atoms that make up your cells. Magnetars occasionally have what we call starquakes, where the crust of the neutron star shifts slightly. These events release enormous bursts of energy, briefly making the magnetar the brightest object in the galaxy, even though it's only 20 kilometers across. The universe is full of extremes, like places where physics operates at the absolute limits of what's possible. Magnetars, black holes, the surfaces of neutron stars, the cores of active galactic nuclei, and yet, despite these extremes, the universe is also full of quiet places. Vast regions of empty space where almost nothing happens, where a few hydrogen atoms drift in darkness, light years from the nearest star. Both extremes exist. Both are part of the whole. If your eyes are closed, keep them closed. If they're open, let them be heavy. I think about the people on Earth sometimes, the billions of people going about their lives, mostly unaware of the cosmic context in which they exist. They know intellectually that Earth is a planet orbiting a star in a galaxy full of stars, but it's not something they feel in their bones. Out here, you feel it. You understand. In a deep, nonverbal way, how small we are, how fragile, how unlikely, and yet also how significant. Because we're the part of the universe that knows, that understands, that asks questions and seeks answers and creates meaning. We're not insignificant. We're the universe becoming conscious of itself. That's not a small thing. Every person who has ever lived is part of this cosmic story. Every thought ever thought, every emotion ever felt, every act of kindness or cruelty, every moment of beauty or pain, all of it is part of the universe's ongoing experience of itself. You are part of that. You matter. Let that knowledge comfort you as you drift toward sleep. The white dwarf I saw earlier, the core left behind by a red giant, will cool slowly over billions of years. It will fade from white to yellow to red to black, though it will never quite reach true black in the current age of the universe. These black dwarfs, as they're called, will be some of the last objects remaining in the far future of the universe, after all the normal stars have burned out, after even the smallest red dwarfs have exhausted their meager supplies of hydrogen. In a universe 100 trillion years old, black dwarfs will still exist, cold and dark, but still there, still made of matter, still holding mass, still warping space-time around themselves with their gravity. And then, eventually, even they will decay. Protons are not perfectly stable. They have a half-life that's almost unimaginably long, but it's finite. Given enough time, all matter will decay into radiation. The universe will end, if end is the right word, as a thin soup of photons and neutrinos spread so far apart that they almost never interact, existing at temperatures just barely above absolute zero. That's trillions upon trillions of years in the future, but it's the ultimate fate of everything. All the stars, all the galaxies, all the black holes, everything. Unless we're wrong, unless there's something we don't understand yet, some new physics that changes the equation. The universe has surprised us before. Don't need to worry about any of this. Just let it be background music to your rest. I'm thinking now about the atoms in my body, the ones that came from supernovas, specific atoms that were once inside specific stars. The iron in my blood might have come from a supernova that exploded 8 billion years ago. That same atom might have been part of several different stars before ending up in the molecular cloud that formed our sun and solar system. It might have been part of asteroids and planets that formed and were destroyed and formed again, and now it's part of me, carrying oxygen through my bloodstream, enabling my existence. In a few decades, maybe a century at most, that atom will be part of something else. It will continue its journey through the universe, part of the endless cycle of transformation that characterizes existence. Nothing is permanent. Everything is borrowed. We're temporary arrangements of stardust, given the gift of consciousness for a brief moment, before we dissolve back into the cosmic whole. That could be frightening, but I find it comforting. We're not separate. We're not isolated. We're part of the great continuity of the universe, Let sleep come now. Let yourself dissolve into rest. The last light of dying stars is not an ending, it's a transformation. The light carries energy outward into space, warming dust grains, exciting atoms, creating the soft glow of nebulae that will eventually collapse into new stars. The material left behind, whether it's a white dwarf or a neutron star or a black hole, continues to affect its environment. Its gravity shapes the orbits of any remaining planets or asteroids. Its magnetic field creates zones of activity in the surrounding space. Even in death, stars remain active participants in the cosmic dance. And the elements they've forged, the heavy atoms created in their cores and scattered by supernovas, those elements make possible a richer, more complex universe. They enable rocky planets and water and organic chemistry and life. We exist because stars die. Our existence is proof that death is not the end, but a transition, a passing of the torch to new forms, new possibilities. The universe is not running down toward a cold, dark end, at least not yet. It's still young, still vital, still full of star formation and planetary birth, and probably, almost certainly, life arising in countless places we'll never know about. We're living in a golden age of the universe, a time when stars still burn bright, when galaxies still swirl with activity, when the cosmic background radiation is still warm enough. Enjoy this moment, this brief, precious moment of warmth, and your breathing is so slow now, so steady. That's perfect. I'm going to let you rest now, friend. The universe will still be here when you wake. The stars will still be shining, the galaxies still turning, the great cycle of birth and death and rebirth continuing as it has for billions of years and will for billions more. You are held by forces larger than you can imagine. Gravity cradles you. The solidity of matter, the resistance of electrons to being compressed, keeps you from collapsing. The weak nuclear force enables the fusion that powers the sun, that warms your world. The strong nuclear force holds atomic nuclei together against the repulsion of protons. You are supported by the fundamental structure of reality itself. You are safe. Let your last conscious thoughts drift away like photons escaping a dying star. Let yourself fall into the deep darkness between stars, where rest is perfect and complete. The last light of dying stars carries a message that endings are not failures but fulfillments, that death gives way to new life, that the universe knows how to transform loss into possibility. Take that message with you into sleep. Hold it gently in your heart. The stars are singing you to sleep now with light that left them long ago, crossing the void to arrive at just this moment, to find you here, ready to... Good night, dear friend. May your dreams be as vast and beautiful as the cosmos itself. May you wake refreshed, renewed, and ready to be your own small miracle in this great unfolding universe. Rest now. The night will hold you. The stars will watch over you.